Uh, Welcome everybody to the NITheCS Mini-School on Elementary Introduction to the Set Theory by Amartya Goswami and Zurab Janelidze. And today is the lecture 4 in this mini-series, and without further ado, I'm just passing down to them. And please make use of Q&A facility to ask questions, or there are not so many of us, you can also raise your hand and we can give you right to ask a question. Thank you. Zurab and Amartya.
Thank you so much, Ilya. Thank you. So Zurab, maybe we first mention those axioms which we didn't yet mention before we discuss something else. What do you think?
We could, yeah. But the other thing I was thinking about, maybe we could ask the audience if there is anything specific they want to see and they haven't seen. Yeah.
Yes. So may we ask our participants that please feel free to write in Q&A, or even you raise your hand and please suggest anything you like us to discuss here, and also some other questions around this elementary set theory which we haven't discussed yet or even touched yet at all. So please feel free to use either Q&A section or raise your hand, and then Ilya will allow you to use your microphone.
So while they're thinking about it, I would like to propose another question, actually, maybe even before we look at further axioms. And that is the following. How to define an infinite set? So it is not too difficult to say what a finite set is. We could try to build it recursively, say that it needs to have either no elements or maybe one element. So basically to use counting for that. And then one could try to define an infinite set as something that is not finite, so as a negation of being finite. But there is actually a very elegant way of defining an infinite set without using counting. And I would like to propose this question for the audience to give some ideas, if they have any ideas on that.
Yeah, that's a very good idea.
Yeah, the reason why this question is important is because set theory as a mathematical theory. So, I mean, in the first lecture, we discussed that set theory has these two aspects. On one hand, it's the language for formalizing all of mathematics, but on the other hand, it's also a mathematical theory where you prove some interesting facts about sets. So, as a mathematical theory, it's very much the theory of infinite sets. Somehow, if you only limit yourself with finite sets, you don't really get to do a lot of interesting set theory unless you specialize in specific areas of mathematics where finite sets are important, of course, like, for example, combinatorics. You can definitely do a lot of combinatorics with finite sets, but not set theory itself. So since set theory is very much about the theory of infinite sets, then it makes sense to address this question of what is an infinite set.
So you are saying that we are asking for a definition of infinite set in terms of the theory what we have developed so far.
That's right.
Yeah. Okay. Any suggestions from the participants? So please feel free to type it up, and if it is too complicated to type it up, please raise your hand, and then it will be maybe easier to speak.
So maybe while they're thinking, maybe I'm going to remind one notion which will be needed for this, and that is the notion of a one-to-one mapping. So if you have two sets, well, first of all, it might be useful to recall how one defines a function in the formal set theoretic setup. So a function from a set X to a set Y, and I think we already touched on this topic. It's just a reminder. Is a subset of the Cartesian product and let me remind you that this is the set of all ordered pairs where X comes from X and Y comes from Y, such that the usual requirement holds. So we think of this as the variable X to which the function is applied, and then the variable Y represents the value of the function. And if Y, a specific Y, is a value of the function at X, then that pair belongs to the set R. So for example, in the case when the function is f of x equals x squared, where x can be any real number, we can think of this as the set of ordered pairs x squared. So this is how we encode a function as a set of ordered pairs. And the condition is that for every x, there must be
a unique Y.
A unique Y such that
the pair should be there.
That's right, such that the pair is in the set R. And then an injective function and another name for it is a function that's a one-to-one mapping.
Yeah, but not use the word one-to-one correspondence, because that's generally used for the bijection.
That's right, yeah. So it's a function such that whenever x1y and x2y are both in R, this is meant to say whenever. So whenever this holds, we have that x1 equals x2, which of course would not be true in this example of x squared, because you've got two different x1 and x2, namely 1 and -1, for which the y value is the same. And here we're disallowing that possibility for two different x values. So if two different x values have the same y value, then these x values must be same themselves. So this notion of an injective function will be useful in defining an infinite set. And now we can go back to the proposals from the audience.
Paul has a question on chat. I think, yeah, it's on chat about defining natural numbers, right?
So is there a more elegant way than simply continuing ad infinitum in the same way that we defined any finite set? Yes, so there is much more elegant way than that. And so that's the question we're asking, but it seems like nobody has answered so far. Maybe there is one here.
Sorry, there is also option in Q&A.
Q&A, yeah.
So it says, is a set that is not finite and it may be countable or uncountable. So, so first, that definition requires first to define what a finite set is. But as we said, I mean, at least we defined finite sets in terms of first defining numbers and counting. And so the question is how to do all of that. Even before we introduce numbers in set theory, we can actually define in a very elegant way, using just this notion of an injective function, what an infinite set is. And the definition is as follows. A set X is infinite when there exists a set Y such that three conditions hold. First condition says that Y is a subset of X. The second condition says that Y is not equal to X. And the third condition says that there is an injective function from X to Y. Now, let's try to understand intuitively why this should be the case.
Simon has a
Simon's suggestion is not bad, but it makes use of natural numbers.
Yeah.
And we say we want to do it as the first thing without having to deal with numbers yet.
Yeah, and this is very much similar what we were discussing in our last lecture, and Partho also suggested about using the Schroeder-Bernstein theorem, which is eventually what we have discussed.
Yeah, so because of that theorem, it will turn out that once there is an injective function from X to Y, because there is also one from Y to X, it's just including mapping every Y to itself, then actually it will actually turn out that X and Y are bijective to each other.
Bijective, yes, yes.
So why does this definition make sense? The thing is that if you take a finite set, right? Let's say set of numbers 1, 2, 3, 4, 5, 6, and 7. So if this is our original set X, right? And then you try to find a subset of X, which is not equal to X. So I mean, subset means that you only can keep elements of X. You cannot introduce more elements, but it mustn't be equal to X. So at least one of the elements must be excluded, right? So let's say, which one shall we exclude, Amartya?
Maybe the last one, just one is sufficient, right?
So let's say we exclude the last one. So we have all the numbers from 1 to 6. Okay, so now the first two conditions are satisfied for this Y. Y is a subset of X. Y is not equal to X. But there is no injective function from X to Y. No matter how we try to map elements of X to Y, because there are more here, we will not be able to get this one-to-one mapping. For example, if we just mapped it straightforwardly, then the problem is that we have nowhere to map 7.
Yeah.
So
at least two of them must be mapped to 1.
Yeah. So the finite sets do not have such a Y. But now let's demonstrate that intuitively that infinite sets will have such a Y, and then let's take this the case of natural numbers. So now if our set is infinite, 0, 1, 2, 3, 4, and so on, and let's say we pick a subset of that set that is not equal to the set.
Yeah.
Remember, the definition asks that there must exist such a set Y. Yeah?
Actually, Simon, basically now we are following what you are saying.
So can we find a set Y which is going to be a subset of this, not equal to it, but nevertheless there will be an injective function from X to Y? And for example, we could take
even numbers. Yeah, let's take even numbers.
Okay, let's take even numbers. So maybe I'll have a more.
Yeah, we need some more numbers. Yes.
So we could take just the even numbers. Even that will do, because the way we can map this injectively now would be to map 0 to 1 to 2. Sorry, 1 to 4, 2 to 6. Well, if it's even numbers, we should probably also have included 0. So then we can just map 0 to 0,
0 to 0,
1
yes.
to 2, 2 to 4, 3 to 6. So it's basically multiplication by 2, right? So every number n is mapped to 2 times n. And this function, the 2n function, basically, right? So the function that maps n to 2n, which is a function from the set of natural numbers to the set of natural numbers. It's injective because if f of x1 equals f of x2.
Zurab, it's a natural number to 2n.
No. Oh, yeah, sorry, yeah. We wanted the function to be into the subset, right? Yeah. Thank you, yeah. So this function that maps n to 2n, if 2x1 is equal to 2x2, right? So this means that 2x1 equals 2x2. Then, of course, we divide by 2 and we get that x1 equals x2. So
and according to our definition of injectivity, it's an injection.
Yeah. And so these two examples should illustrate why is this the right definition. And now after this, one of the things you would want to prove in set theory, as a theory, I mean, if you want to build up the theory of infinity, one of the things to prove would be that this definition is equivalent to the one saying that it's a set that's not finite. So it's a set that is not bijective to any of the finite sets where finite sets are explicitly built out of natural numbers.
There is a question in the chat. Oh, kind of.
Yeah, thank you, Ilya. I'm going to come back to that question just now. And then it turns out that proving that this notion of infinite set is the same as the one that, for example, Shimon was suggesting, proving that will be a theorem that is not completely trivial. So you will have to develop some lemmas before you can establish that fact. Okay, so the question on the chat, is this not us creating different infinities by definition? I'm not sure I understand the question. Maybe, do you understand the question, Marta?
We can think it as a different example of an infinite set, but what do you mean by different infinities? Because
yeah, I think maybe Paul can ask this question.
Yeah, I allow Paul to talk. Paul, can you please unmute yourself and give a comment?
Oh, he doesn't have a microphone at this moment.
Okay, maybe you could expand in the chat. Thank you.
Okay. Thank you, Paul.
But sorry, also Zurab, don't your definition also apply to the uncountable sets? I think it's also applicable.
Yeah, it's applicable to any infinite set, not just the countable ones.
Yeah.
Because our definition is actually definition, or rather set theoretic definition of an infinite set. And of course, Ilya, you are right that uncountable set is also an infinite set. So it should also work. Otherwise, it contradicting the definition itself.
Okay. Now, sizes of sets were mentioned a few times, and I think we did say this before, but with the notion of injective function, we can maybe make things a bit more clear now. So here is another definition of the size of a set. We say that the cardinality of a set Y is larger or equal to the cardinality of a set X, which will be written as this way. When there exists an injective function from X to Y. And we can also define the cardinality being strictly larger so when equality is not allowed. Which is then written as with a strict inequality simple when it is bigger or equal to, but there is no bijection. From X to Y. And what is a bijection? A bijection is an injection that's also surjective. So a bijection from X to Y is an injection from X to Y. So let's call this F, such that for every yeah, there exists X in X such that F of X equals Y.
Yeah. Zurab, Paul has managed to write it down, his questions in a more elaborative way on the chat.
Wonderful, wonderful. I'm going to now say one more thing and then come back to the question. Yeah. So then it turns out that you can start with any set X, and you get create a set out of it which has strictly larger cardinality than X by taking the power set of that set. And then you can continue this way, and always, because it happened once, then by iterating power set construction, always you get something strictly bigger than the previous step. And this is true not only for the case when X is finite, but even for infinite sets. So this way, we will get an infinite collection of infinite sets, all of whose cardinalities are increasingly bigger.
Strictly different. Yeah.
And if we start with X equals the set of natural numbers, right? Then this is what we usually call countable, when a set has cardinality that's equal to the cardinality of the natural numbers. And uncountable can be any of these. But the next level there, so it turns out that the cardinality of the set of natural numbers, I think this we already mentioned before, the next level is the same as the cardinality of real numbers. And that's what usually is called continuum, but then you can get further and further cardinalities, even bigger and bigger, just by taking power sets. And so these are the kind of theorems you want to prove in building up set theory as a theory. And that was basically the work that Georg Cantor did. So Georg Cantor worked on set theory as basically as the theory, because there was no other theory before that, is the theory of infinite sets. While his friend and collaborator Richard Dedekind worked on set theory as a universal language for mathematics. So this is as much as at least I've been able to gather information or heard about this from other mathematicians and so on, as a universal language for mathematics. For example, the definition of a function given here, this definition, first was formulated by Richard Dedekind. Before, people thought of functions more as some kind of expressions you perform on a variable. And
a
third name to be mentioned here, Ernst Zermelo, was the first to write out axioms for set theory. And then after that, there are many other people that should be mentioned, but these three were kind of the starting point of major contributions to set theory. Shall we go back to this explanation now?
There was a question which now disappeared. Px is the power set of x. Yes, that is true. And now we may address Paul's questions, which is in the chat.
Maybe we can add this to the notes here. This is the power set of x, which is defined as the set of all s's such that s is a subset of x.
Right. Yeah, Paul's question is about these limit things, which we actually not have any kind of limit in that sense of analysis.
Yeah, I think maybe Paul is still thinking about functions as expressions. So, set theoretically thinking, you imagine that you've got in front of you an infinite collection of objects, and here is another infinite collection of objects. And we don't care about any limits here. We just have this collection of things, an array of things put next to each other in an infinite line. And we observe that this infinity has a portion that's basically the same amount as the original one, because we've been able to establish this one-to-one mapping from the first one to the second one, which is in fact in this case even a bijection.
Yes. So basically, we are not actually introducing any kind of, although we have infinite sets in this sense, which we completely defined in terms of set theory.
In terms of
this concept of limit of a function, what we generally see in first in calculus or in analysis later on, we are not actually have any kind of limit concept here in that sense of infinite, what when we generally said n tends to infinity here. Here, basically, we have different examples of infinite sets, and we see there is some kind of nice relationship or bijections like or injections or different levels of infinite sets, but not in the sense of the limit what we consider in this analysis case.
Yeah, and the question of how to define one being bigger than another, that we answered here. But I see that maybe Paul will be able to join by phone and maybe ask his question again. Voice. Okay. All right. So there is, I mean, so the theory of set theory, as I said, has been largely worked out by Georg Cantor. Then it obtained axiomatic foundations, so one could rigorously develop the theory further. And the first foundation, axiomatic one, was given by Zermelo.
Sorry, Zurab.
Yes.
I allowed Paul to talk because I'm not sure. Have the Paul finished with his question, and did he want to ask some clarification? I'm not sure.
I think once he has the microphone, he can ask.
Yeah, I think now he has. Paul. At least he's unmuted. Paul, can you ask a question? Do you want to ask a question?
You might have to wait until we can hear him.
Okay, it still doesn't work. Okay.
Okay, good. Sorry.
Unfortunately, there will be no next week with this set theory,
maybe,
but you can always write it out.
We never had these Kumo sessions. Maybe we should actually after this lecture, because this is the last lecture, right?
Yes. Yeah.
So Paul, you're welcome to join on the Kumo space if you will sort out your microphone, and then we'll be there. We can talk about this further there. So Dedekind was more concerned about the kind of phrasing the mathematics in the language of set theory. And then after we figured out that, okay, so all of mathematics can be formalized inside set theory, other contexts came about which are also able to formalize all of mathematics. And one such is that of category theory. And since we had mini school on category theory last year, I thought that it would be good if I could maybe show here the link of how to construct a category out of the world of sets, so that that category will be as suitable for formalizing all of mathematics as is the universe of sets.
Yeah. So maybe we just recapitulate the definition of category itself, because may not be all the participants here were also there, as well as it's a long time ago before we actually show this association.
Yeah, I mean, I wouldn't want to go into general definition of a category. I would just want to explicitly describe what is the category of sets, which is all we need for this purpose. So the difference between the category of sets and the universe of sets is the following. So we have this notion of the universe of sets. Well, not the, but a universe of sets. And every time we have a universe of sets, it gives rise to the category of sets. And the difference is that in a universe of sets, the fundamental relationship between objects, which are sets, is that of belonging as an element. And we agreed to draw an arrow. At some point, I think we mentioned this, that one way to represent when, let's say, a set X is an element of a set Y. And then that, of course, means that we will only have at most one arrow between every two objects. And we could have a situation like this, where X is element of Y and Y is element of Z, and that does not imply that X is element of Z. So we cannot really kind of compose these arrows together to get an arrow across. An example is, let's take X to be the empty set, Y is the set whose only element is the empty set, and Z is the set whose only element is the set with the only element being the empty set. So if we consider these three sets, this empty set is the element of that, and that one is the element of the further set. But as you see, that set only has one element, which is this thing, and that's not the same as that. So it's not true that empty set is an element of that other set. Now, when we build the category of sets there, our fundamental objects are still sets, but arrows no longer mean that one set is an element of the other set. We still have arrows there, but they mean something else. An arrow from X to Y is a function.
In the above sense.
In the sense we defined today, yes. And if I have two functions, f and g, I can compose them.
Here's a big difference compared to the belongs to.
Right. And so, I mean, I'm not going to go into what a category is because we had a separate set of videos for that. But the idea is that when viewing sets from the point of view of a category, there the fundamental objects are sets, but the fundamental connections between objects are functions. And the operation of composition of functions is the language in which all of mathematics can be phrased. Whereas from the point of view of a universe of sets, the objects are still sets, but the fundamental connections between sets are the element relationships. And all of mathematics can be formalized using just this single element relationship. So this is the difference between the two. But it turns out that you can just as well formalize mathematics with functions being as your starting point, which is maybe not so difficult to guess, because you can actually already define element using functions, since you take a set with just one element, and you take any set X, and by specifying a function from a single element set to X, you basically you're basically isolating an element. So you can, in fact, if this was your starting point, you could redefine elements as functions from a singleton set to X, because their values are determined uniquely by an element. And moreover, we can even define this using just arrows. A set having only one element is the same, so a singleton set is a set S such that for any set Y, there is exactly one function.
From Y to that set.
Yeah. From Y to S. And it's kind of obvious why there should be exactly one function, because there's only one element. So if you want to build a function from Y to there, you will have to map everything here. And moreover, it turns out that this property defines what a singleton set is. So
and
you
similarly,
can go back here.
We can also define empty set here, just like opposite way.
Yeah, and we can define the empty set, and we can define all sorts of things. So this allows us to transition between the two languages. I mean, how to transition from this language to that language, we already saw. We just take, we just define functions the way we did today. But if you started with if one started with the language of a category with suitable axioms, which I'm not going to go into now, then one can transition back to set theory by defining the element relationship in this way. It's not going to work perfectly, but it works well enough that one can transition between the two worlds. And both of the worlds are can be then seen as foundations for all of mathematics. Okay. So maybe towards the end of this session, we could do what we said we would do. At least you suggested, Amartya, we should do that. So listing some of the other axioms on the universe of sets which we haven't listed before. So these axioms will be the Zermelos Axioms. There are further axioms introduced by other mathematicians after Zermelo, but we will leave them out. We're not going to go into that.
I think we talked up to power set axiom, if I recollect it correctly.
So those axioms which we already listed in the first session, I'm just going to give them names. I'm not going to go into detail. So equality of sets axiom. This tells you that sets can be distinguished from each other just by knowing what elements they have. If the two sets have the same elements, they must be the same set. Then existence of the empty set. So there exists a set that doesn't contain any elements. This we already talked about as well. Then we had the power set axiom, saying that for every set, power set exists. And then we had the pairing axiom. Okay, maybe it's worth reminding here that if this one says if X is a set, then this thing here
is also a set.
The collection of all subsets of X, there is a set whose elements are exactly the subsets of X. That's what this axiom says.
is also a set.
Maybe I should put some if then here. So if the X is a set, then this set exists. Huh? The pairing axiom says that if A and B are sets, then the ordered pair of A and B, which is defined as the following set, maybe I'll put A there, and this exists. Okay, so in addition to these, Zermelos also has the following axioms. So these are the ones that we did discuss before.
Mm-hmm.
Then we have something called the Union Axiom, which says that if X is a set, if X exists as a set, so in other words, for every set X, the following thing, which is called union of X, also exists. So this will be all the X's, or maybe A's, such that A is an element of X, which is an element of capital X, or some small x. So if you think about it, if this is your set X, we look at all of its elements. These are the small x's. And then we expand each of them. And their elements we call A's. And then we are requiring that this whole thing together itself is a set. So we can take the union of elements of X. And then we have something called restricted comprehension. We discussed why general comprehension does not work, that it gives a paradox. So it says that if X is a set, then for any property, let's say phi of S about sets, the set of those elements in X that satisfy phi is a set. So here one has to be a bit careful how to phrase this, because we need the notion of a property. A property will be something that's expressible in the formal language of set theory. We haven't discussed the formal language of set theory with all the logical symbols we are allowed to use and so on. So subject to that imprecision, we are formulating this axiom here. But intuitively, it is a very, very good demonstration. So we discussed that if I just have some random collection of sets, there's no guarantee that this thing will be a set. So this is the collection of all the x's for which phi of x is true. But we do require that the overlap. So I don't know if this collection will be a set or not, but if I already have some other set X, then among those things that I don't know if it's a set or not, if I just pick those which fall in my existing set X, then that thing should be a set. Did I explain it well enough, Marta?
Yeah, maybe we give a concrete example, then maybe it will be easier.
I mean, in other words, it's to say that if X is a set and C a collection of sets, then the set of those x's in X which belong also to the collection
of the C should be
is a set. So, for example, let's say we already know that integers, that natural numbers, form a set. Then, thanks to this axiom, I will be able to build a set of even numbers. How? I will say, okay, now let's pick those m's in n for which, such that m equals to 2n for some n in n. Then I know that the even numbers also form a set thanks to restricted comprehension. So I can, whatever portion of n I can describe, like here's the portion of x I'm describing, whatever portion of n I can describe, that portion will also form a set.
So here the property is this multiple of 2 in the above sense.
Yeah. And then another axiom is that there exists an infinite set. This axiom one might not want to keep all the time, because maybe sometimes you want to not restrict yourself like that. Maybe you want to allow possibility of there not existing an infinite set. And then there is something called the axiom of choice.
Which sometimes you have a choice to take or not to take.
So there are many ways of formulating the axiom of choice. One of them is to say that given a surjective function, from x to y, and I think we already defined what a surjective function was.
Yes, on the right hand side.
Well, we defined what a bijection was. So
and
this part, if this part together with the injectivity gives us bijection, but this part on its own is called surjectivity. So that's when every element in your codomain, in your set Y, can be reached by some element from the domain. So there's always some x such that f of x equals y. So given a surjective function from x to y, let's call this function, let's say g.
There exists a function from y to x.
There exists f from y to x.
Such that the composition.
Such that if I compose them, if I take fg, gf for every y will equal y, for every y. And the reason why this is called axiom of choice is that we can draw a picture of the following kind. So imagine we have a function from x to y, so that every y can be reached. That's what we said, right? But it means if every y can be reached, it means that every y has some non-empty pre-image. Right?
Map to that point.
And these pre-images cannot intersect each other, because you cannot have like one element mapping to two different things. Because then it's not a function.
Contradict the definition. Contradict the definition of the function.
Yeah. So this is the function g, a picture for the function g, and from the picture we can say, okay, if each of these balloons are non-empty, then of course we could go back. We could go back by picking for each of these. So let's say for this first one, we just pick a random element here, and we define that to be f of x. So if that's x, I'll define f of x to be a random element from this balloon. And I'll do the same thing for each element. And the reason why this doesn't follow from other axioms that you can actually describe a function like this is because you might have to make infinitely many choices here. You might have a large number of these, and you have to kind of say that for each thing I'm going to make a random choice. But then you end up discovering that you can't express this construction using the axioms already introduced. So you need a new axiom guaranteeing, a new axiom guaranteeing that such f does exist. And the reason why you want to actually pick something from the balloon is because when you apply G back, it should give you your original element. So I want, because things that map back to X are exactly these ones. So if I'm deciding for a value of f of X, so that when I apply G to it, it gives me back X, and maybe I should have called that thing Y. Let me actually fix my notation, because I was using X for element of X and so on. So if I've got a Y and I'm deciding what f of Y should be, whatever f of Y is, I want G of that to equal Y. So it must be one of the things in this balloon. So that's the illustration for the axiom of choice.
Or equivalently, one can say that the existence of this map F for a given surjective map is equivalent to this axiom what we have mentioned there.
Yeah, so this is one of the ways of phrasing the axiom of choice. There are also other ways of phrasing the axiom of choice, but that's a separate story. We're not going to detail that. And if I'm not mistaken, these are the, yeah?
In fact, there is even a book on axiom of choice itself. So those who are interested to know very detailed of various aspects of axiom of choice, I forgot the name of the author, but if you Google, you can find it.
There is something called Zorn's lemma, which is used a lot in mathematics, and that requires axiom of choice.
Like so, the product of, I mean, there are many places, like in topology, you need axiom of choice for the product of compact spaces, infinite product. Ring theory, you need axiom of choice for existence of these maximal ideals. I mean, there are various places where it's indispensable in some sense.
So these are the basic axioms, and then a couple of others have been added by other mathematicians. For example, there is Frankel's axiom, and that's why set theory is usually called Zermelo-Frankel set theory, because it's Zermelos axioms together with Frankel's axiom. Also, von Neumann contributed. In some cases, it's also not even clear who contributed first and so on. Certainly, there was nobody before Zermelo, but after Zermelo, there were some duplications every now and then. But I also want to mention one additional axiom that was introduced a bit later, which is Grothenbeck's axiom of universes. And the reason why I want to mention this is the following. So first of all, what does the axiom say? We described what a universe of sets is, and intuitively, this axiom says that in our universe of sets, so if this is our universe of sets, no matter what set you pick, you will always be able to find a mini universe inside which your set lives. So you'll get a chain of universes like that, and it could be an infinite chain. Now, Grothendieck used this axiom because to develop category theory in the language of set theory, Zermelos axioms are not enough. You need to kind of go at the next level of the universe, at least a few steps. So he introduced this axiom for his foundation of algebraic geometry based on category theory. And then when the final piece for proving Fermat's last theorem was complete by Andrew Wiles, he used a lot of mathematics that was developed during 20th century. One of them was Grothendieck's work that deals with categories. And so he implicitly makes use of Grothendieck's axiom of universes. Fermat's last theorem hasn't really been proved in the Zermelo-Frankel context. It has been proved in a context with Grothendieck's axiom. However, after that, a few papers came out that discuss exactly which aspect of Grothendieck's axiom is needed, and that you can actually weaken it. And there are some works discussing whether, to what extent you can get rid of this completely and so on. But in the original approach of Andrew Wiles, he was making use of this axiom without caring too much about it, because he just made use of results of Grothendieck that made use of the axiom. So anyway, so I'm just trying to say that the story of axiomatics is not just something that stays in the past. With the advancement of mathematics, when we solve unsolved problems and so on, every now and then we need to come back to the axiomatics and see what axioms are we making use of, or maybe we need more axioms than we had so far, and try to introduce them to see if they can solve the problem or not.
In fact, Grothenbeck need to make this build this setup even to solve another problem, which is well conjecture. So it looks like that we had some axiomatic setup for the set theory, but even to solve the problems, we actually built new axioms, or rather we need new axioms to solve these problems. And here are two problem-oriented questions which actually require these additional axioms. One is to solve well conjecture by Delin actually, and Grothenbeck did, where they use these Grothenbeck axioms inverse of course. And then, as you mentioned, Andrew Walsh also has used it to solve another problem, which is this formalized theorem. So set theory is always with us, and this axiomatic systems is always with us in some sense.
Yeah, and another thing I want to add in terms of giving historical background is that, so Emmy Noether was very much a lot of mathematics that she herself gave a lot of credit to Richard Dedekind for many of her ideas in abstract algebra. And there is this standard phrase that this was already in Dedekind. And so she was certainly inspired by set theory, because she would call her approach to abstract algebra, and this is a very significant achievement of hers, because a lot of abstract algebra was developed after her contributions to the subject. I think many consider her as the kind of the mother of abstract algebra. So she would use the terminology set theoretic approach. Which was the idea of formalizing ideas of algebra in the language of set theory, something that Dedekind already started, and then taking this language further to introduce new concepts, like, for example, concepts of a ring, for instance, as a mathematical structure, and she developed some aspects of module theory and so on. And so this set theoretic approach, based on the idea of using the language of set theory, opens up new possibilities for formalizing ideas that previously was not a possibility. And so that's the impact that set theory has made on mathematics. I mean, of course, we gave a very brief kind of description of the impact, but at least we touched on some of the major points, I hope.
Yeah. Zurab, maybe we should stop because it's 4 o'clock, and ask our participants if they have any questions. In the chat, is possible we get assessment regarding set theory to verify my understanding? You have some set of lecture notes and exercises, Zurab, right, on your website to
I do,
practice? Yes.
Yes.
So maybe you paste the link here again in chat quickly, so that Paulus can immediately. Yeah, here it is, Paulus. So maybe.
And anyone watching, anyone here or watching this video afterwards is welcome to email your solutions to the exercises you'll find on the website to us.
Thank you everybody for listening our discussions, and thank you for joining us and all your questions, and I hope you have enjoyed it. And, okay, over to you, Ilya.
Thank you very much, Amartya and Zurab, for the very nice mini school.